topology, and then you travel back and forth proving theorems by just doing one aspect in characteristic theory or reduce mod P, prove the other aspect, and go back again and so on and so on. Okay, now I'm going to discuss with you one of the motivating aspects. It's the definition of an abelian variety. Let me tell you, I was once working in Oslo in Norway, and that was long, long before we had computers. And the secretary was typing out my manuscript and couldn't read my handwriting, which is quite usual for most people. And I had the word abelian varieties, and she said, I don't know this word abelian. I don't know this word, you couldn't read it. I said, but that says abelian. She said, but I've never heard of abelian. And then I said, there's a famous mathematician, and his statue is in the center of Oslo. Ah, she said, you mean all. So there's no reason you have to say abelian varieties. But we say abelian varieties. So abelian varieties, you have a variety, which means irreducible, and it is a group object, so you can add points, and the variety is projective. And mind, by projective, I mean closed in projective space. So, for example, the affine line, which has a group structure, just adding points, is not an abelian variety because it's not closed in the projective space. Or the group GLN of n by n matrices, right? It's given by n by n matrices, and moreover, the determinant is non-zero. That's certainly not a projective variety. But an abelian variety is projective or complete, like you want to say in classical analytic language, or proper in the terminology of Grothendieck. It's irreducible and the points form a group. A remark, the conditions imply that the group law in A is commutative, and I will not prove that for you. If you interrupt me, you don't understand this, the proof, then I will say, sorry, that's hard. And some people think that this is the origin of the name abelian, but that's not true. Niels Henrik Abel computed integrals on the Riemann surface. So you take a Riemann surface of G is 3, say, you take 2 points, you take a differential, and you want to compute the integral from A to B of omega. But you don't tell which paths you take from A to B. And that's not well defined, because the path may go as straight as possible, but it also may wind around all the holes and the loops and so on, and then compute the integral. So that integral is not well defined, but if you mod out all periods, that's to say all integrals of all differentials over all loops which are closed, if you divide that out, then you get something which is an abelian variety. So Niels Henrik Abel found that integrals on Riemann surfaces have their natural values in an abelian variety. I will introduce for you the name torsion point. So G is an abelian group. Mine is an abelian group, otherwise it doesn't make much sense. And I take, for G square brackets n, all points annihilated by n. Torsion dividing n. And the union of all the n torsion is called the torsion of G. And because the group is abelian, the product of two torsion elements, of course, is torsion. An exercise for those of you who have never given a class in algebra, please provide a finite group, please provide a group which is an element of order 2 and an element of order 3 where the product is not finite order. And the people doing modular 4 of course know exactly what example I have in mind. But that's part of it. Okay, so this is the torsion point. And for the abelian variety, I consider the torsion points on that abelian variety. Now mind that my abelian variety can be over some small field. So in my whole talk, I will work over a field K, and then I will go up to an algebraic closure, because if you want to see points you have to go to a large field sometimes, right? And the torsion point, so what I do, I take all k value points of A, and that's a group. That group has finite order elements, and the unit of this vector torsion. Okay, so you see, I really want to work over a field which is not necessarily algebraically closed, because that's always the bridge between the various geometries. So for arithmetic reasons and for application in number theory, you really have to view all kinds of fields. And let me run ahead of myself and explain you one nice aspect. Suppose you have an elliptic curve over Q, and you have another elliptic curve over Q. And suppose that these curves are isomorphic over the complex numbers. Are these curves isomorphic over Q? Well, the whole proof of Fermat-Lab theorem, the whole proof of Andrew Wiles, 93-95, of Fermat-Lab theorem hinges on the fact that arithmetic properties of elliptic curves over Q are basic tools which you need. So what I'm saying, that if you have an elliptic curve and you know all properties of the curve of the complex numbers, that doesn't tell you anything about the arithmetic properties of your curve. And that is the essence why you really want to restrict to epistemic fields. I'll go very fast through 4 different examples of being varieties. And one which you all know, I hope, is you take a curve of degree 3, and I take a point on there which I fix. Perhaps he doesn't like elliptic curves. And on such a curve, I can find an addition. You connect A and B, then you get a third point, S. You connect S with the chosen base point, and you take the third intersection, that's A and B. And it's a beautiful theorem that this indeed makes a cubic curve which is non-singular and with a chosen base point as a group variety. Actually, this is the being variety, it's the being variety dimension 1, and every being variety dimension 1 is an elliptic curve. And let me warn you, some people say a cubic curve in P2 non-singular is an elliptic curve, and that's wrong. What am I omitting? I'm omitting the base point. And there's a beautiful example of Selmer, who provided us with the following example. You take this cubic equation and you take the zeros of it. What do I mean by zeros? By zeros I mean you go to any extension field and solve this equation to 0, right? Now, what is the beauty of this example? This is a cubic curve, no doubt. And the beauty of the example is that Selmer proved that this is defined over Q. And Selmer proves that if you, well, it's also defined over Z, you can reduce mod n, where n is any integer, and then it does have points. You can go to the reals, and then it does have points. But the Q points do not exist. So this is a beautiful example of a curve where there are no base point choice possible, and this is not an elliptic curve. Okay, so let me go to, thank you. Let me go to the next example. If you have a being variety of the complex numbers, you can take its tangent space and you can take an exponential map in the sense of complex Lie groups, and you can take its kernel And you easily prove that this, of course, is c to the power g. G is always my dimension of my being variety. That this is a lattice, and this is isomorphic to z to the power 2g, right? And that this defines your A of c. So the A of c is nothing c to the g mod lambda. What do I mean isomorphic? Well, of course, I only mean this as a complex variety. I mean, the left-hand side is a complex variety, the right-hand side is a complex variety, and it's isomorphic as complex varieties. And this you know very well for G equal 1. For G equal 1, you have the y plus p function, and that does it because you know that the B variety dimension 1 can be put in standard form. The standard form is the differential equation of the y plus p function, and that gives you the parameterization. Right? And this is an example of complex form. Please remember this formula because I'll use it, first of all. Second of all, remember that this is very strong if you work over complex numbers. Quotation marks has no value if you work over number fields. Right? And let me explain to you that this exponential map is a transcendental map. So for example, an extremely hard question is, suppose you have a point here. It comes from a point here. Suppose you know arithmetic properties of the starting point. Can you know anything about the value under the exponential map? And you all know the difficulty if you know that sinus, the sine function of beta, right, is a rational number. Does it imply that beta is rational? No, of course. And so on, so on, so on. So this formula is extremely strong over complex numbers. In arithmetic, it's of almost no use. And the big enterprise which John Tate did, and for which he basically obtained his medal in Oslo, is that he gave a substitute for this parameterization with the help of Tate modules. And I've written a paper about that, and if you want to read it, you can really see what is the essence of that. Okay, and there's a, so this is what I want to say. So this is our plus p function, this is an elliptic curve. The geometry topology of EC are well understood, but the arithmetic of E is really hard. Then, for G bigger than 1, there is complex tori, which are not algebraizable, but that theory is very well understood by now. Okay, the third point is we follow AML in the sense that we make all the values of integrals on a Riemann surface. And they land into an abelian variety with this Jacobian. And the Jacobian for a curve of G to G is an abelian variety dimension G. So you can produce lots and lots and lots of abelian varieties by just sitting down, write an equation of a curve, show it's non-singular, and then take the Jacobian. And then so this might comment that elliptic curves are abelian varieties, and these are the only abelian varieties which have dimension 1. And the second comment is the Jacobian of a curve reflects the cohomology of the curve. So if you compute cohomology, that's just an algebraic technique. Can you do a lot of theory with it? And the beautiful fact is that if you go to the Jacobian tells you what the cohomology is, but moreover, the Jacobian has a geometry. So the Jacobian of the curve reflects cohomology of the curve, the geometry makes the abstract algebra related to the curve geometric. And this point of view has a lot of applications. And then I have a fourth example that is abelian varieties of a finite field. And there's a theorem by underway. I will not explain this. This I will explain next Thursday in my seminar talk. if you have a Wien variety, then raising coordinates to the q's power, where q is the number of elements in your field, gives you an endomorphism of your Wien variety. Of course, because the Wien variety is given by equations over fq, and if you raise the power, if you raise the coefficient to the q's power and the coordinates to the q's power, that's just the q's power of the whole equation, because you're working characteristic p. So this point again lands onto the Wien variety. And this gives you an endomorphism, nature given for any Wien variety. And it was a beautiful idea of André Weil to compute the absolute value of the embedding of pi a in the complex numbers. And actually, by a Lefschetz fixed point formula analog to characteristic p, he proved this, and this is one of the starting points of a lot of algebraic geometry. Honda and Tate have proved that conversely, if you take a Rhine number, then you can construct a Wien variety, and it's an open problem whether the proof of the Honda-Tate theory reduces complex uniformization with all the drawbacks can be made algebraic. And I think GB and I made progress last week that we really can prove this, but I don't announce this yet. So in the Honda-Tate theory, the only known proof uses complex uniformization of this beautiful theorem of Honda and Tate, and that proves really involved. Okay, let me move on. I'm going to prove for you that the torsion points of a Wien variety are Zariski dense. And what I'm wiping out now is basically the proven characteristic zero, but let me give you a proof of this theorem. You know, I have to give at least one proof. So, K is any field. It sits in a greatly closed field, and I take the torsion points of A, right? And that's my set gamma if you want. I take the Zariski closure of it. Now you know why I don't take the classical topology, because this may be over a finite field or whatever, right? And this of course sits in A, and the claim is that this equals A. So the torsion points are dense. And what's the proof? Well, I don't know this yet, so let's call this G. And this G sits in A, and it has a connected component of the identity. And I can take an N which has greatest common divisor N with the characteristic of K, which might be P or 0, I don't care, and with what I call the index of G in G0. Right? And then I look at the G0 torsion points by N. And because of this condition, this is the same as G index N. And of course it is the same as AK torsion N, because that's my construction. Right? Now I go back. There's a theorem which says that the torsion points are z mod n to the power of 2G on the right dimension G if that number N is not divisible by the characteristic. So we know that this group, right, that this group is isomorphic to z mod n to the power 2 times the dimension of G, on one hand. On the other hand, it is the torsion on N, so it's also z mod n to 2 times the dimension of A. So the conclusion is the dimension of G is the dimension of H of A. Conclusion, G is A. Okay, so that's that is the starting point. I think this is a good time for a break. I'm sorry, I'm a few minutes late. The next hour I will discuss this money number and just share it with the other. Okay, thank you very much.
We will take a short 5-minute break and anybody interested to come back after 5 minutes. I would like to also advertise the seminar talk that Frans just announced. There will be a talk on the Honda tape theory this Thursday at 4 o'clock.
And I don't guarantee everybody understands the first half.